Hi, this is Lab 3. So the purpose of this lab is to make observations on a computational model simulating a black hole. Using GlowScript, this lab uses fundamental physics principles to model a black hole to find its mass and then find the initial velocity of a spaceship that gets close to it without crashing. These principles include the momentum principle, which explains how an object will change its motion under a net force, and it can be observed that at a constant speed, the system will move in a straight line under no net force as acceleration is zero. Newton's second law explains how the acceleration of an object is proportional to the mass of it and the net force acting on it. Additionally, the universal law of gravitation states that all objects attract each other with a net force that is directly proportional to the product of their masses and inversely proportional to the square of their distance. Lastly, you have the net force decomposed into its parallel and perpendicular components. The parallel is the direction of the motion and describes speeding up or slowing down, while perpendicular describes the curving motion or magnitude of momentum times velocity squared divided by radius, which points towards the center of the circle. So in the computational model, the system is the spaceship and the planet, while the surroundings includes everything else around the system. So the code used a while loop in the code to find the mass of a black hole using initial conditions like the mass of the star. There is also code to show the increasing and decreasing force of the parallel and perpendicular components throughout the eclipse in the arrows. So the results were that Fnet was 7.46 times 10 to the 28th, and you can see the components as well. In the computational model, the position update formula is of importance as it allows us to predict what the change in position is over time velocity. Also, using this model requires us to make some assumptions, including how gravitational force is the only force acting between the star and the black hole. Also, the parallel component of the net force was assumed to be equal to the magnitude of initial momentum subtracted from the final momentum divided by change in time. In part 2, the mass of the black hole that was found in part 1 was used. I found the gravitational force exerted by the black hole and shift on the planet, and the planet and the black hole and the ship separately using the formulas mentioned in the beginning. The results of part 2 are shown on the right, with the ship's trajectory deflected by the black hole in a slingshot manner without crashing into it. Additionally, I used trial and error to find the initial velocity. The x and y components of the initial velocity suggest that the spaceship was moving left and upwards, with magenta showing the spaceship's path and cyan showing the planets. And the shortest distance that I found was about a few percent of the radius of the planet's orbit around the black hole, which was 1.96 times 10 to the 11th meters. To further think about the physics concepts in this lab, we can look at the discussion questions. So for the first question, the net force and its parallel and perpendicular components are different from the rate of change in momentum. While approximation is accurate for small iterations of delta P, it would deviate if there are additional uncertainties in the experiment. Regarding the next question, to enter an orbit around the black hole for prolonged observation, the x component of the initial velocity would have to be smaller, while the y component would be larger. Also, there are different sources of error in the experiment, including both theoretical and systematic ones. Through the use of non-relativistic momentum, errors from part 1 may have also carried over to part 2 when finding the initial velocity. Nonetheless, the results and data collected demonstrate that computational models are powerful tools that can simulate real-world conditions with various parameters and find unknown values. Thank you.